Eulerian video magnification for revealing subtle changes in the world. Figure 1, an example of using our Eulerian video magnification framework for visualizing the human pulse. A. 4 frames from the original video sequence, face. B. The same 4 frames with the subject's pulse signal amplified. C. A vertical scan line from the input, top, and output, bottom. Videos plotted over time shows how our method amplifies the periodic color variation. In the input sequence, the signal is imperceptible, but in the magnified sequence, the variation is clear. The complete sequence is available in the supplemental video. Abstract. Our goal is to reveal temporal variations in videos that are difficult or impossible to see with the naked eye and display them in an indicative manner. Our method, which we call Eulerian video magnification, takes a standard video sequence as input and applies spatial decomposition, followed by temporal filtering to the frames. The resulting signal is then amplified to reveal hidden information. Using our method, we are able to visualize the flow of blood as it fills the face and also to amplify and reveal small motions. Our technique can run in real time to show phenomena occurring at temporal frequencies selected by the user. See our categories: I.4.7 Image Processing and Computer Vision, Scene Analysis, Time Varying Imagery. Keywords: Video-based rendering, spatiotemporal analysis, Eulerian motion, motion magnification. Links: DL PDF Web. 1. Introduction. The human visual system has limited spatiotemporal sensitivity, but many signals that fall below this capacity can be informative. For example, human skin color varies slightly with blood circulation. This variation, while invisible to the naked eye, can be exploited to extract pulse rate. Similarly, motion with low spatial amplitude, while hard or impossible for humans to see, can be magnified to reveal interesting mechanical behavior. The success of these tools motivates the development of new techniques to reveal invisible signals in videos. In this paper, we show that a combination of spatial and temporal processing of videos can amplify subtle variations that reveal important aspects of the world around us. Our basic approach is to consider the time series of color values at any spatial location, pixel, and amplify variation in a given temporal frequency band of interest. For example, in Figure 1, we automatically select and then amplify a band of temporal frequencies that includes plausible human heart rates. The amplification reveals the variation of redness as blood flows through the face. For this application, temporal filtering needs to be applied to lower spatial frequencies, spatial pooling, to allow such a subtle input signal to rise above the camera sensor and quantization noise. Our temporal filtering approach not only amplifies color variation, but can also reveal low-amplitude motion. For example, in the supplemental video, we show that we can enhance the subtle motions around the chest of a breathing baby. We provide a mathematical analysis that explains how temporal filtering interplays with spatial motion in videos. Our analysis relies on a linear approximation related to the brightness constancy assumption used in optical flow formulations. We also derive the conditions under which this approximation holds. This leads to a multi-scale approach to magnify motion without feature tracking or motion estimation. Previous attempts have been made to unveil imperceptible motions in videos, analyze and amplify subtle motions, and visualize deformations that would otherwise be invisible. Propose using the cartoon animation filter to create perceptually appealing motion exaggeration. These approaches follow a Lagrangian perspective in reference to fluid dynamics, where the trajectory of particles is tracked over time. As such, they rely. Figure 2. Overview of the Eulerian video magnification framework. The system first decomposes the input video sequence into different spatial frequency bands and applies the same temporal filter to all bands. The filtered spatial bands are then amplified by a given factor, alpha, added back to the original signal, and collapsed to generate the output video. The choice of temporal filter and amplification factors can be tuned to support different applications. For example, we use the system to reveal unseen motions of a digital SLR camera caused by the flipping mirror during a photo burst camera. Full sequences are available in the supplemental video. on accurate motion estimation, which is computationally expensive and difficult to make artifact-free, especially at regions of occlusion boundaries and complicated motions. Moreover, Liu et al. 2005 have shown that additional techniques, including motion segmentation and image in painting, are required to produce good quality synthesis. This increases the complexity of the algorithm further. In contrast, we are inspired by the Eulerian perspective, where properties of a voxel of fluid, such as pressure and velocity, evolve over time. In our case, we study and amplify the variation of pixel values over time in a spatially multiscale manner. In our Eulerian approach to motion magnification, we do not explicitly estimate motion, but rather exaggerate motion by amplifying temporal color changes at fixed positions. We rely on the same differential approximations that form the basis of optical flow algorithms. Temporal processing has been used previously to extract invisible signals and to smooth motions. For example, Poe et al. 2010 extract a heart rate from a video of a face based on the temporal variation of the skin color, which is normally invisible to the human eye. They focus on extracting a single number, whereas we use localized spatial pooling and bandpass filtering to extract and reveal visually the signal corresponding to the pulse. This primal domain analysis allows us to amplify and visualize the pulse signal at each location on the face. This has important potential monitoring and diagnostic applications to medicine, where, for example, the asymmetry in facial blood flow can be a symptom of arterial problems. Fuchs et al. 2010 use per-pixel temporal filters to dampen temporal aliasing of motion in videos. They also discuss the high-pass filtering of motion, but mostly for non-photorealistic effects and for large motions, figure 11 in their paper. In contrast, our method strives to make imperceptible motions visible using a multi-scale approach. We analyze our method theoretically and show that it applies only for small motions. In this paper, we make several contributions. First, we demonstrate that nearly invisible changes in a dynamic environment can be revealed through Eulerian spatiotemporal processing of standard monocular video sequences. Moreover, for a range of amplification values that is suitable for various applications, explicit motion estimation is not required to amplify motion in natural videos. Our approach is robust and runs in real time. Second, we provide an analysis of the link between temporal filtering and spatial motion and show that our method is best suited to small displacements and lower spatial frequencies. Third, we present a single framework that can be used to amplify both spatial motion and purely temporal changes, e.g., the heart pulse, and can be adjusted to amplify particular temporal frequencies, a feature which is not supported by Lagrangian methods. Finally, we analytically and empirically compare Eulerian and Lagrangian motion magnification approaches under different noisy conditions. To demonstrate our approach, we present several examples where our method makes subtle variations in a scene visible. 2. Spacetime video processing. Our approach combines spatial and temporal processing to emphasize subtle temporal changes in a video. The process is illustrated in Figure 2. We first decompose the video sequence into different spatial frequency bands. These bands might be magnified differently because a. They might exhibit different signal-to-noise ratios, or b. They might contain spatial frequencies for which the linear approximation used in our motion magnification does not hold. Sect. 3. In the latter case, we reduce the amplification for these bands to suppress artifacts. When the goal of spatial processing is simply to increase temporal signal-to-noise ratio by pooling multiple pixels, we spatially low-pass filter the frames of the video and downsample them for computational efficiency. In the general case, however, we compute a full Laplacian pyramid. We then perform temporal processing on each spatial band. We consider the time series corresponding to the value of a pixel in a frequency band and apply a bandpass filter to extract the frequency bands of interest. For example, we might select frequencies within 0.4-4 Hz, corresponding to 24-240 beats per minute if we wish to magnify a pulse. If we're able to extract the pulse rate, we can use a narrow band around that value. The temporal processing is uniform for all spatial levels and for all pixels within each level. We then multiply the extracted bandpass signal by a magnification factor, alpha. This factor can be specified by the user and may be attenuated automatically according to guidelines in SECT. 3.2. Possible temporal filters are discussed in SECT. 4. Next, we add the magnified signal to the original and collapse the spatial pyramid to obtain the final output. Since natural videos are spatially and temporally smooth, and since our filtering is performed uniformly over the pixels, our method implicitly maintains spatiotemporal coherency of the results. 3. Eulerian motion magnification. Our processing can amplify small motion even though we do not track motion as in Lagrangian methods. In this section, we show how temporal processing produces motion magnification using an analysis that relies on the first-order Taylor series expansions common in optical flow analyses. 3.1 First-order motion. To explain the relationship between temporal processing and motion magnification, we consider the simple case of a 1D signal undergoing translational motion. This analysis generalizes directly to locally translational motion in 2D. Let I, x, t denote the image intensity at position x and time t. Since the image undergoes translational motion, we can express the observed intensities with respect to a displacement function, delta t, such that I, x, t equals f x plus delta t and I, x, 0 equals f x. The goal of motion magnification is to synthesize the signal. The estimated intensity at position x and time t is a function of a shifted position. For some amplification factor, alpha. Assuming the image can be approximated by a first-order Taylor series expansion, we write the image at time t f x plus delta t in a first-order Taylor expansion about x as. The intensity at position x and time t is approximately a function of x plus a time-dependent perturbation. Let B, x, t be the result of applying a broadband temporal bandpass filter to I, x, t at every position x, picking out everything except f, x in EQ, 2. For now, let us assume the motion signal, delta t, is within the passband of the temporal bandpass filter. We will relax that assumption later. Then we have b of x, t equals the Dirac delta function of t times the partial derivative of f of x with respect to x. In our process, we then amplify that bandpass signal by alpha and add it back to I, x, t, resulting in the process signal. The modified intensity is the original intensity plus a scaled background. Combining x, 2, 3, and 4, we have the approximate intensity at position x and time t is a function of x plus a time-dependent derivative term. Assuming the first-order Taylor expansion holds for the amplified larger perturbation, 1 plus alpha delta t, we can relate the amplification of the temporally bandpass signal to motion magnification. The processed output is simply the approximated intensity at position $x and time $t is a function of $x plus a scaled delta function of $t. This shows that the processing magnifies motions the spatial displacement, delta t, of the local image, f, x, at time t, has been amplified to a magnitude of 1 plus alpha. This process is illustrated for a single sinusoid in Figure 3. For a low-frequency cosine wave and a relatively small displacement. Figure 3. Temporal filtering can approximate spatial translation. This effect is demonstrated here on a 1D signal, but equally applies to 2D. The input signal is shown at two-time instants, I, x, t equals f, x, at time t, and I, x, t plus 1 equals f, x plus delta, at time t plus 1. The first-order Taylor series expansion of I, x, t plus 1, about x, approximates well the translated signal. The temporal bandpass is amplified and added to the original signal to generate a larger translation. In this example, alpha equals 1, magnifying the motion by 100%, and the temporal filter is a finite difference filter, subtracting the two curves. Delta t, the first-order Taylor series expansion, serves as a good approximation for the translated signal at time t plus 1. When boosting the temporal signal by alpha and adding it back to I x t, we approximate that wave translated by 1 plus alpha delta. For completeness, let us return to the more general case where delta t is not entirely within the passband of the temporal filter. In this case, let delta subscript kt, indexed by k, represent the different temporal spectral components of delta t. Each delta subscript kt will be attenuated by the temporal filtering by a factor, gamma subscript k. This results in a bandpass signal. B of x, t equals the sum over k of gamma k times delta k of t times the partial derivative of f of x with respect to x. Compare with EQ 3. Because of the multiplication in EQ 4, this temporal frequency-dependent attenuation can equivalently be interpreted as a frequency-dependent motion magnification factor, alpha subscript k equals gamma subscript k alpha, resulting in a motion magnified output. The approximated intensity at point x and time t is a function of x plus a sum of terms. The result is as would be expected for a linear analysis. The modulation of the spectral components of the motion signal becomes the modulation factor in the motion amplification factor, alpha subscript k, for each temporal subband, delta subscript k of the motion signal. 3.2 bounds. In practice, the assumptions in sect. 3.1 hold for smooth images and small motions. For quickly changing image functions, i.e., high spatial frequencies, f, x, the first-order Taylor series approximations becomes inaccurate for large values of the perturbation, 1 plus alpha delta t, which increases both with larger magnification, alpha, and motion, delta t. Figures 4 and 5 demonstrate the effect of higher frequencies, larger amplification factors, and larger motions on the motion-amplified signal of a sinusoid. As a function of spatial frequency, omega, we can derive a guide for how large the motion amplification factor, alpha, can be, given the observed motion, delta t. For the process signal, I x t, to be approximately equal to the true magnified motion, I caret x t, we seek the conditions under which the approximation of I tilde by I hat implies an approximation of a function plus a scaled derivative by a shifted function. Figure 4. Illustration of motion amplification on A1D, signal for different spatial frequencies, and alpha values. For the images on the left side, lambda equals 2 pi and delta 1 equals pi over 8 is the true translation. For the images on the right side, lambda equals pi and delta 1 equals pi over 8. A. The true displacement of I x 0 by 1 plus alpha delta t at time t equals 1, colored from blue, small amplification factor, to red, high amplification factor. B. The amplified displacement produced by our filter, with colors corresponding to the correctly shifted signals in A. Referencing EQ 14. The red, far right, curves of each plot correspond to 1 plus alpha delta t equals lambda over 4 for the left plot, and 1 plus alpha delta t equals lambda over 2 for the right plot, showing the mild, then severe, artifacts introduced in the motion magnification from exceeding the bound on 1 plus alpha by factors of 2 and 4, respectively. Figure 5. Motion magnification error, computed as the L subscript 1, norm between the true motion amplified signal, figure 4a, and the temporally filtered result, figure 4b, as function of wavelength for different values of delta t, a, and alpha b. In A, we fix alpha equals 1, and in B, delta t equals 2. The markers on each curve represent the derived cutoff point, 1 plus alpha delta t equals lambda over 8, EQ 14. Let f x equals cos omega x for spatial frequency, omega, and denote beta equals 1 plus alpha. We require that the cosine of omega x minus a term is approximately the cosine of omega x plus that term. Using the addition law for cosines, we have the cosine of omega x minus beta omega delta t sine omega x equals the cosine of omega x cosine beta omega delta t minus sine omega x sine beta omega delta t. Hence, the following should approximately hold. Cosine of beta omega delta t is approximately 1, and sine of beta omega delta t is approximately beta delta t omega. The small angle approximations of x, 12 and 13, will hold to within 10%, for beta omega delta t less than or equal to pi over 4. The sine term is the leading AP. Figure 6. Amplification factor, alpha, as function of spatial wavelength lambda for amplifying motion. The amplification factor is fixed to alpha for spatial bands that are within our derived bound, EQ, 14, and is attenuated linearly for higher spatial frequencies. Approximation, and we have sin pi over 4 equals 0.9 pi over 4. In terms of the spatial wavelength, lambda equals 2 pi over omega of the moving signal. This gives the product of 1 plus alpha and delta of t is less than lambda over 8. EQ 14 above provides the guideline we seek, giving the largest motion amplification factor, alpha, compatible with accurate motion magnification of a given video motion, delta t, and image structure spatial wavelength, lambda. Figure 4b shows the motion magnification errors for a sinusoid when we boost alpha beyond the limit in EQ 14. In some videos, violating the approximation limit can be perceptually preferred, and we leave the lambda cutoff as a user-modifiable parameter in the multiscale processing. 3.3 Multiscale analysis. The analysis in sect. 3.2 suggests a scale-varying process. Use a specified alpha magnification factor over some desired band of spatial frequencies, then scale back for the high spatial frequencies found from EQ 14 or specified by the user, where amplification would give undesirable artifacts. Figure 6 shows such a modulation scheme for alpha. Although areas of high spatial frequencies, sharp edges, will be generally amplified less than lower frequencies, we found the resulting videos to contain perceptually appealing magnified motion. Such effect was also exploited in the earlier work of Freeman et al. 1991 to create the illusion of motion from still images. For results. The results were generated using non-optimized MATLAB code on a machine with a 6-core processor and 32 GB RAM. The computation time per video was on the order of a few minutes. We used a separable binomial filter of size 5 to construct the video pyramids. We also built a prototype application that allows users to reveal subtle changes in real time from live video feeds, essentially serving as a microscope for temporal variations. It is implemented in C++, is entirely CPU-based, and processes 640 by 480 videos at 45 frames per second on a standard laptop. It can be sped up further by utilizing GPUs. A demo of the application is available in the accompanying video. The code is available on the project webpage. To process an input video by Eulerian video magnification, there are 4 steps a user needs to take. 1. Select a temporal bandpass filter. 2. Select an amplification factor, alpha. 3. Select a spatial frequency cutoff, specified by spatial wavelength, lambda subscript c, beyond which an attenuated version of alpha is used. And 4. Select the form of the attenuation for alpha, either force alpha to 0 for all lambda subscript c, or linearly scale alpha down to 0. The frequency band of interest can be chosen automatically in some cases, but it is often important for users to be able to control the frequency band corresponding to their application. In our real-time application, the amplification factor and cutoff frequencies are all customizable by the user. Figure 7. Eulerian video magnification used to amplify subtle motions of blood vessels arising from blood flow. For this video, we tuned the temporal filter to a frequency band that includes the heart rate, 0.88 Hz, 53 BPM, and set the amplification factor to alpha equals 10. To reduce motion magnification of irrelevant objects, We applied a user-given mask to amplify the area near the wrist only. Movement of the radial and ulnar arteries can barely be seen in the input video, A, taken with a standard point-and-shoot camera, but is significantly more noticeable in the motion-magnified output, B. The motion of the pulsing arteries is more visible when observing a spatiotemporal YT slice of the wrist, A and B. The full wrist sequence can be found in the supplemental video. Figure 8. Representative frames from additional videos demonstrating our technique. The videos can be found in the accompanying video and on the project webpage. We first select the temporal bandpass filter to pull out the motions or signals that we wish to be amplified, step 1 above. The choice of filter is generally application dependent. For motion magnification, a filter with a broad passband is preferred. For color amplification of blood flow, a narrow passband produces a more noise-free result. Figure 9 shows the frequency responses of some of the temporal filters used in this paper. We use ideal bandpass filters for color amplification, since they have passbands with sharp cutoff frequencies. Low-order IR filters can be useful for both color amplification and motion magnification, and are convenient for a real-time implementation. In general, we used two first-order low-pass IR filters with cutoff frequencies, omega subscript L and omega subscript H, to construct an IR bandpass filter. Next, we select the desired magnification value, alpha, and spatial frequency cutoff, lambda subscript C, steps 2 and 3. While EQ 14 can be used as a guide, in practice, we may try various alpha and lambda subscript C values to achieve a desired result. Users can select a higher alpha that violates the bound to exaggerate specific motions or color changes at the cost of increasing noise or introducing more artifacts. In some cases, one can account for color clipping artifacts by attenuating the chrominance components of each frame. Our approach achieves this by doing all the processing in the YQ space. Users can attenuate the chrominance components, I and Q, before conversion to the original color space. For human pulse color amplification, where we seek to emphasize low spatial frequency changes, we may force alpha equals 0 for spatial wavelengths below lambda subscript C. For motion magnification videos, we can choose to use a linear ramp transition for alpha, step 4. Figure 9. Temporal filters used in the paper. The ideal filters, A and B, are implemented using DCT. The Butterworth filter, C, is used to convert a user-specified frequency band to a second-order IR structure and is used in our real-time application. The second-order IR filter, D, also allows user input. These second-order filters have a broader passband than an ideal filter. We evaluated our method for color amplification using a few videos, 2 videos of adults with different skin colors and one of a newborn baby. An adult subject with lighter complexion is shown in face, figure 1, while an individual with darker complexion is shown in face 2, figure 8. In both videos, our objective was to amplify the color change as the blood flows through the face. In both face and face 2, we applied a Laplacian pyramid and set alpha for the finest 2 levels to 0. Essentially, we downsampled and applied a spatial low-pass filter to each frame to reduce both quantization and noise, and to boost the subtle pulse signal that we are interested in. For each video, we then passed each sequence of frames through an ideal bandpass filter with a passband of 0.83 Hz to 1 Hz, 50 BPM to 60 BPM. Finally, a large value of alpha is almost equal to 100 and lambda subscript C is almost equal to 1000 was applied to the resulting spatially low-pass signal to emphasize the color change as much as possible. The final video was formed by adding this signal back to the original. We see periodic green to red variations at the heart rate and how blood perfuses the face. Baby 2 is a video of a newborn recorded in situ at the nursery department at Winchester Hospital in Massachusetts. In addition to the video, we obtained ground truth vital signs from a hospital-grade monitor. We used this information to confirm the accuracy of our heart rate estimate and to verify that the color amplification signal extracted from our method matches the photoplethysmogram. an optically obtained measurement of the perfusion of blood to the skin, as measured by the monitor. Figure 10. Selective motion amplification on a synthetic sequence, Sim4 on left. The video sequence contains blobs oscillating at different temporal frequencies, as shown on the input frame. We apply our method using an ideal temporal bandpass filter of 1-3 Hz to amplify only the motions occurring within the specified passband. In B, we show the spatio-temporal slices from the resulting video, which show the different temporal frequencies and the amplified motion of the blob oscillating at 2 Hz. We note that the space-time processing is applied uniformly to all the pixels. The full sequence and result can be found in the supplemental video. To evaluate our method for motion magnification, we used several different videos: face, figure 1, sim 4, figure 10, wrist, figure 7, camera, figure 2, face 2, guitar, baby, subway, shadow, and baby 2, figure 8. For all videos, we used a standard Laplacian pyramid for spatial filtering. For videos where we wanted to emphasize motions at specific temporal frequencies, e.g., in Sim 4 and guitar, we used ideal bandpass filters. In Sim 4 and guitar, we were able to selectively amplify the motion of a specific blob or guitar string by using a bandpass filter tuned to the oscillation frequency of the object of interest. These effects can be observed in the supplemental video. The values used for alpha and lambda subscript c for all of the videos discussed in this paper are shown in Table 1. For videos where we were interested in revealing broad but subtle motion, we used temporal filters with a broader passband. For example, for the Phase 2 video, we used a second-order IR filter with slow roll-off regions. By changing the temporal filter, we were able to magnify the motion of the head rather than amplify the change in the skin color. Accordingly, alpha equals 20, lambda subscript c equals 80 were chosen to magnify the motion. By using broadband temporal filters and setting alpha and lambda subscript c, according to EQ 14, our method is able to reveal subtle motions, as in the camera and wrist videos. For the camera video, we used a camera with a sampling rate of 300 Hz to record a digital SLR camera vibrating while capturing photos at about 1 exposure per second. The vibration caused by the moving mirror in the SLR, though invisible to the naked eye, was revealed by our approach. To verify that we indeed amplified the vibrations caused by the flipping mirror, we secured a laser pointer to the camera and recorded a video of the laser light, appearing at a distance of about 4 meters from the source. At that distance, the laser light visibly oscillated with each exposure, with the oscillations in sync with the magnified motions. Our method is also able to exaggerate visible, yet subtle motion, as seen in the baby, Phase 2, and subway videos. In the subway example, we deliberately amplified the motion beyond the derived bounds of where the first-order approximation holds in order to increase the effect and to demonstrate the algorithm's artifacts. We note that most of the examples in our paper contain oscillatory movements, because such motion generally has longer duration and smaller amplitudes. However, our method can be used to amplify non-periodic motions as well, as long as they are within the passband of the temporal bandpass filter. In shadow, for example, we process a video of the sun's shadow moving linearly yet imperceptibly over 15 seconds. The magnified version makes it possible to see the change. Table 1. Table of alpha, lambda subscript c, omega subscript l, omega subscript h, values used to produce the various output videos. For Phase 2, 2 different sets of parameters are used, one for amplifying pulse, another for amplifying motion. For guitar, different cutoff frequencies and values for alpha, lambda subscript c are used to select the different oscillating guitar strings. F subscript s is the frame rate of the camera, even within this short time period. Finally, some videos may contain regions of temporal signals that do not need amplification, or that, when amplified, are perceptually unappealing. Due to our Eulerian processing, we can easily allow the user to manually restrict magnification to particular areas by marking them on the video. This was used for face and wrist. 5. Discussion. Sensitivity to noise. The amplitude variation of the signal of interest is often much smaller than the noise inherent in the video. In such cases, direct enhancement of the pixel values will not reveal the desired signal. Spatial filtering can be used to enhance these subtle signals. However, if the spatial filter applied is not large enough, the signal of interest will not be revealed. Figure 11. Assuming that the noise is zero mean white and wide-sense stationary with respect to space, it can be shown that spatial low-pass filtering reduces the variance of the noise according to the area of the low-pass filter. In order to boost the power of a specific signal, e.g., the pulse signal in the face, we can use the spatial characteristics of the signal to estimate the spatial filter size. Let the noise power level be sigma to the power 2, and our prior on signal power over spatial frequencies be s lambda. We want to find a spatial low-pass filter with radius r, such that the signal power is greater than the noise in the filtered frequency region. The wavelength cutoff of such a filter is proportional to its radius r, so the signal prior can be represented as sr. The noise power, sigma to the power 2, can be estimated by examining pixel values in a stable region of the scene, from a gray card, or by using a technique as in. Since the filtered noise power level, sigma to the power 2, is inversely proportional to r to the power 2, we can solve the following equation for r. The variance sr equals k times the variance divided by r squared, where k is a constant that depends on the shape of the low-pass filter. This equation gives an estimate for the size of the spatial filter needed to reveal the signal at a certain noise power level. Eulerian versus Lagrangian processing. Because the two methods take different approaches to motion, Lagrangian approaches explicitly track motions, while our Eulerian approach does not. They can be used for complementary motion domains. Lagrangian approaches, e.g., work better to enhance motions of fine-point features and support larger amplification factors, while Figure 11. Proper spatial pooling is imperative for revealing the signal of interest. A frame from the face video, Figure 1, with white Gaussian noise, sigma equals 0.1 pixel, added. On the right are intensity traces over time for the pixel marked blue on the input frame, where B shows the trace obtained when the noisy sequence is processed with the same spatial filter used to process the original face sequence, a separable binomial filter of size 20, and C shows the trace when using a filter tuned according to the estimated radius in EQ 15, a binomial filter of size 80. The pulse signal is not visible in B, as the noise level is higher than the power of the signal, while in C, the pulse is clearly visible, the periodic peaks about 1 second apart in the trace. Our Eulerian method is better suited to smoother structures and small amplifications. We note that our technique does not assume particular types of motions. The first-order Taylor series analysis can hold for general small 2D motions along general paths. In Appendix A, we further derive estimates of the accuracy of the two approaches with respect to noise. Comparing the Lagrangian error, epsilon subscript L, EQ 29, and the Eulerian error, epsilon subscript E, EQ 31, we see that both methods are equally sensitive to the temporal characteristics of the noise, N subscript T, while the Lagrangian process has additional error terms proportional to the spatial characteristics of the noise, N subscript X, due to the explicit estimation of motion, EQ 27. The Eulerian error, on the other hand, grows quadratically with alpha and is more sensitive to high spatial frequencies, I subscript XX. In general, this means that Eulerian magnification would be preferable over Lagrangian magnification for small amplifications and larger noise levels. We validated this analysis on a synthetic sequence of a 2D cosine oscillating at 2 Hz temporally and 0.1 pixels spatially with additive white spatiotemporal Gaussian noise of 0 mean and standard deviation, sigma. Figure 12. The results match the error-to-noise and error-to-amplification relationships predicted by the derivation, Figure 12b. The region where the Eulerian approach outperforms the Lagrangian results, Figure 12a left, is also as expected. The Lagrangian method is more sensitive to increases in spatial noise, while the Eulerian error is hardly affected by it, Figure 12c. While different regularization schemes used for motion estimation that are harder to analyze theoretically may alleviate the Lagrangian error, they did not change the results significantly, Figure 12a right. In general, our experiments show that for small amplifications, the Eulerian approach strikes a better balance between performance and efficiency. Comparisons between the methods on natural videos are available on the project webpage. 6. Conclusion. We described a straightforward method that takes a video as input and exaggerates subtle color changes and imperceptible motions. To amplify motion, our method does not perform feature tracking or optical flow computation, but merely magnifies temporal color changes using spatiotemporal processing. This Eulerian-based method, which temporally processes pixels in a fixed spatial region, successfully reveals informative signals and amplifies small motions in real-world videos. Acknowledgements. We would like to thank Guha Balakrishnan, Steve Lewin-Berlin, and Neil Wadhwa for their helpful feedback and the SIGGRAPH reviewers for their comments. We thank Salu and Diching Sun for helpful discussions on the Eulerian versus Lagrangian analysis. We also thank Dr. Donna Brzezinski, Dr. Karen McAlman, and the Winchester Hospital staff for helping us collect videos of newborn babies. This work was partially supported by DARPA Scenic Program, NSF CGV 1111415, and Quanta Computer. Michael Rubenstein was partially supported by an NVIDIA Graduate Fellowship. A Eulerian and Lagrangian error. We derive estimates of the error in the Eulerian and Lagrangian motion magnification with respect to spatial and temporal noise. The derivation is done again in 1D for simplicity and can be generalized to 2D. We use the same setup as in SECT. 3.1. Both methods approximate the true motion amplified sequence, I(xt), as shown in 1. Let us first analyze the error in those approximations on the clean signal, I(xt), without noise. In the Lagrangian approach, the motion amplified sequence I(L)(xt) is achieved by directly amplifying the estimated motion, delta t, with respect to the reference frame, I(x0). The intensity at a point in time is the initial intensity at a shifted position. In its simplest form, we can estimate delta t in a pointwise manner, see SECT. 5 for discussion on spatial regularization. Delta tilde equals the ratio of partial derivatives of I with respect to t and x, where I subscript x xt equals del I xt slash del x, and I subscript t xt equals I xt minus I x0. From now on, we will omit the space x and time t indices when possible for brevity. The error in the Lagrangian solution is directly determined by the error in the estimated motion, which we take to be second-order term in the brightness constancy equation, although it is usually not paid in optical flow formulations because of Newton iterations. The first equation approximates I, x, t, using a Taylor expansion, and the second rearranges it to solve for I underscore t over I underscore x. The estimated motion, delta t, is related to the true motion, delta t, by. Delta tilde is approximately delta t plus 1/2 delta squared t times I subscript xx. Plugging 19 in 16 and using a Taylor expansion of I about x plus 1 plus alpha delta t, we have. The approximated intensity at a later time is the initial intensity shifted, plus a second-order correction term. Subtracting 1 from 20, the error in the Lagrangian motion magnified sequence, epsilon subscript L, is. The error epsilon L is approximately the absolute value of 1/2 times 1 plus alpha times delta squared of t times I subscript xx times I subscript x. In our Eulerian approach, the magnified sequence, I caret subscript e xt, is. The modified intensity is the sum of the intensity and alpha times the time derivative of the intensity. This also equals the initial intensity plus 1 plus alpha times the time derivative of the intensity. Similar to 4, using a two-tap temporal filter to compute I subscript t. Using a Taylor expansion of the true motion magnified sequence I caret defined in 1 about x, we have the estimated intensity at position x and time t is approximated by a Taylor expansion. Using 18 and subtracting 1 from 23, the error in the Eulerian motion magnified sequence epsilon subscript e is. The error epsilon e is approximately the absolute value of a difference between two terms. With noise, let I to the power xt be the noisy signal such that the observed intensity is the true intensity plus noise. For additive noise n xt, the estimated motion in the Lagrangian approach becomes delta tilde equals the ratio of I prime t to I prime x, which also equals the ratio of it plus nt to ix plus nx, where n subscript x equals del n slash del x and n subscript t equals n x t minus n x 0. Using a Taylor expansion on n subscript t, n subscript x, about 0, 0, 0 noise, and using 18, we have the approximate value of delta t tilde is given by a sum of terms involving delta t and its derivatives. Plugging 27 into 16 and using a Taylor expansion of I about x plus 1 plus alpha delta t, we get the approximate value of I tilde prime L at x. T is the sum of I at x plus 1 plus alpha times delta t at 0, and a complex expression involving ix, id, ixx, nt, nx, and n. Using 19 again and subtracting 1, the Lagrangian error as a function of noise, epsilon subscript L, n, is. The error term epsilon sub L of n is approximately the absolute value of a complex expression involving n, alpha, delta, and I. In the Eulerian approach, the noisy motion magnified sequence becomes. The equation shows two expressions for I tilde prime e of xt. Using 24 and subtracting 1, the Eulerian error as a function of noise, epsilon subscript e n, is. The error epsilon e of n is approximately the absolute value of a polynomial in n, delta, and I. If we set the noise to 0 in 29 and 31, the resulting errors correspond to those derived for the non-noisy signal as shown in 21 and 24.